Hello everyone, welcome you all to MSP lecture series on transfer chemistry. I have been discussing in the last couple of lectures about the classification of ligands by donor atoms, and I completed discussion on hydrogen and we are midway with respect to carbon as donor atom. Let me continue from where I had stopped. In my previous lecture I had initiated discussion about the CO analog CS. So, let me start about the chemistry of carbon thiomonoxide complexes. As I mentioned, unlike carbon monoxide, carbon thiomonoxide is not stable and polymerizes above -160 degree centigrade. So, that means free CS does not exist in a stable form, and however CS compounds can be made using appropriate CS precursors, and then very similar to carbon monoxide CS can be incorporated. There are examples of homolyptic CS complexes also. Let me show you preparation of few carbon thiomonoxide complexes. Before I start writing about the thiomonoxide preparation, let me show you the coordination modes. Coordination modes are pretty similar to what we come across among carbon monoxide complexes. It can comfortably act as a terminal ligand, very similar to carbon monoxide, and since S is soft here, it can readily bind to another soft metal in bridging fashion like this. On the other hand, this carbon can also donate its lone pair to two metal centers with or without metal-metal bond, and it can also bridge 3 metal centers, and also one can anticipate this kind of coordination also in a trimetallic system where sulfur lone pair goes to one metal and carbon takes another metal, and whereas this double bond can bind to another metal. And of course, you can have carbon functioning as a bridged bidentate, and then sulfur can go to another one or one of this fashion. Okay. There are examples in each case. Let me show you a few examples or representative examples. Yeah, further when you look into carbon disulfide, very similar to carbon dioxide, it also shows following coordination modes. You can see simple one, when it binds, this is how it is going to bind, breaking one of the CS double bonds, and then it can also bridge two metal centers in this fashion, eta 2 and mu, and it can also show this kind of coordination, and where you can also come across trimetallic system in this way, or one can also have something like this or this or this one. So, these are some of the standard and well known coordination modes or binding modes of carbon disulfide. Let us look into the preparation of CS complexes. There are at least 2 to 3 very useful precursors are there that can be conveniently used to prepare CS complexes. The simplest one is using carbon disulfide. I deliberately taken two different type of tertiary phosphines here. When you take this iridium tri tertiary phosphine chloride compound, iridium in +1 state, and treat this one with carbon disulfide, so now if you see here, now it is giving a compound very similar to Vasca's compound. This is a trans compound, and here why the sulfur is not abstracted by triphenyl phosphine, rather tritertiary phosphine, because here the one that is more basic, so that would leave to form this sulphide. You should remember, if you have two different type of tertiary phosphines, the one that is better sigma donor will readily get oxidized as a result. So, here forming N-butyl phosphine sulfide and it is abstracting sulfur from CS2. And of course, if we consider another reaction, for example something like this, similar reaction. Now, it does not have any option other than eliminating one of the triphenyl phosphine as triphenyl phosphine sulfide. But when choice is there, the most basic one leaves. This is one method of making CS complexes. Another important method is so this is thioacetate. So, this one also can give so this can also form a compound like this. So, this is very much similar to FeCO3 PME3 twice a 18 electron complex. It is in 0 valent state. So, let us look into another example here. So, dianionic complex. So, here the cation can be sodium. So, if that is the case, I can also see here Na2FeCO4 for example. You take this one and treat this one with, this is thiophosgene. Okay. Phosgene we know it is COCl2. So, we are using thiophosgene CSCl2. This one can also give a compound very similar to FeCO5. So, this one is very similar to FeCO5. So, this comes along with, so if it is 2 sodium are there, NaCl will come out. This is a neat reaction. Only thing is one has to be extremely careful while handling phosgene or thiophosgene, they are very poisonous gases. So, this is the second method. And third method, in fact, we used thioacetate, we used carbon disulfate, we used, and also we used thiophosgene. In another method, carbon disulfate can also be used. For example, let us consider for variety a half sandwich compound of manganese. Suppose we do not have a phosphine here. So, we start with a reaction in which we do not have a phosphine to abstract sulfur from carbon disulfide. In that case, later one can also add a suitable tertiary phosphine to abstract S from CS2 to form CS complexes. So, initially if we add CS2 for this one of the ligands would come out and it forms an intermediate compound of this type. This gives you some idea how CS2 would initially bind to the metal center and eventually it cleaves one of the CS bond. If phosphine is there, it will abstract that sulfur to form phosphine sulfide and hence you get the corresponding CS compound. So, initially it forms a compound like this. Now, we will add a tertiary phosphine. It abstracts the sulfur to form so, this is how one can conveniently use one of the available methods to make these compounds. Let me write one more method of preparation using sodium amalgam. again a state complex. If you treat this complex with sodium amalgam, so this is again an 8 electron species. So these are the few methods that one can conveniently use to make thiocarbon monoxide complexes. And as I mentioned again, thiomonoxide is a relatively good sigma donor and a better pi acceptor compared to carbon monoxide. Before I go, okay, I did mention about orthometallation. This is another important reaction we come across in case of carbon donor ligands, especially when we have phenyl groups are there on a donor atom that is in close proximity to the metal. You can see CH activation, and then there can be some elimination or it can be added oxidatively to form orthometallated compound. The first orthometallated compound was made in 1960 from this reaction. Let me show you the first example of orthometallated compound, that was with palladium with this diazo benzene. So when this organic compound was refluxed in the ethanol with potassium tetrachloropalladate, so it resulted in the elimination of 2 equivalents of HCl to form a compound like this. You can see palladium is in +1 state, +2 state here in both. Okay, this is the first compound which shows orthometallation, and later several orthometallated compounds were made, and also in fact people planned orthometallation reactions. And one disadvantage with this orthometallation is there sometime when you are using some tertiary phosphines, especially having aromatic groups with not having any substituents at ortho position, they can leads to orthometallation and also they can deactivate the catalyst. And one such example is seen with Wilkinson catalyst. For example, if you take Wilkinson catalyst here with rhodium tricytriphenyl phosphine complex, so this can readily form oxidatively added compound through orthometallation, and rhodium is getting oxidized from rhodium 1 to rhodium 3. Just I have shown one of the phenyl groups expanded so that orthometallation can be seen here. Other 2 triphenyl phosphines remain. So something like this. So now you can see, okay, through the CH is added to rhodium, we have rhodium in +3 state, and however there can be reductive elimination, this HCl, like very similar to concerted elimination, that can also happen, and that can leads to the formation of this compound. This, so this is a typical orthomethylation reaction one can see, especially with triphenyl phosphine or any bisphosphine having phenyl substituents, and due to the steric problem, if the phenyl groups comes very close to the metal center and there can be CH activation that can leads to either oxidative addition, and that compound can also be stable or can be stabilized, or eventually if you leave it or if you heat it little bit, the HCl elimination can be seen, or even the elimination can be speeded up by adding a base such as triethylamine. So, triethylamine can abstract HCl to form triethylaminum chloride, and this reaction can proceed to give eventually orthomethylated product. So, one has to be extremely careful for this kind of reactions, and especially when we are using triphenyl phosphine with platinum metals for catalytic purpose. These reactions are quite common and thus can deactivate the catalyst, so that your rate of the reaction decreases dramatically. Now let us look into another interesting ligand system, isocyanates, and isocyanates I have shown the binding mode. Okay. So, you can have either linear fashion it can bind, or it can also show this bent mode here, and the difference can be seen from the bond angle here. It is 165 to 179, we can consider as linear, and if it is in the range of 130 to 135, it will be bent. So, then let us see how these isocyanide compounds are prepared. Isocyanide are again neutral ligands, very similar to carbon monoxide or tertiary phosphines. So, some simple substitution reaction can be performed. This is a general reaction I am going to write. That means by choosing appropriate reaction condition, one can substitute all carbon monoxide on a metal center to form homolytic isocyanide complexes. You take this again 0 valent complex, treat with CNR, one can make homolytic complex. This is very similar to CrCO6 in 18 electron species. So, one can also make this compound. One can also start with a dinitrogen compound. Of course, you may be curious to know how dinitrogen compounds are there. Once I complete the carbon ligands, I shall move on to nitrogen. There I would be elaborating more about nitrogen, preparation of dinitrogen compounds and their reactivity and all those things. If you take bis dinitrogen complex of molybdenum or tungsten, of course here 2N2 comes out. These are some of the important methods of preparation of isocyanide complexes, and let us look into the reactions of isocyanates, that means the reactions of bound isocyanates. What are the reactions one can perform when an isocyanide ligand is coordinated to a metal center? So, three reactions one can think of. One is coupling reaction, one is nucleophilic reaction, and another one is electrophilic reaction. So, let us look into first coupling reaction. Let us take a molybdenum complex treat this one with zinc and wet THF. Wet THF will take care of this one. I am just writing 4 isocyanates on one side to show the coupling reaction. This is a dimeric complex of niobium. When it is treated with isocyanate, of course excess of isocyanate, and now you should remember they have lone pairs intact. These lone pairs will be donated to the other niobium that has 4 chlorides on it. So, these are the examples for coupling reactions one can perform on bound isocyanates. Let us take this one and treat this one with methyl iodide. This is another interesting example for this coupling reaction here. It gives metallated compound of this type. These are the few examples to understand the coupling reactions of isocyanates with various transition metals. One I showed you with molybdenum, and another one I showed you with niobium, and one I showed with homolyptic iron complex, pentaisocyanate iron. So, let us look into reactivity, more reactivity of bound isocyanates in my next lecture. Thank you.